So the topic of the talk is non-interactive zero knowledge, and let's see what I mean. Okay, so zero knowledge, we've talked a lot about it, zero knowledge today. What have we seen? Well, zero knowledge is pretty awesome. I hope we all agree by now. And what Alon showed us in the morning is that zero knowledge actually crucially relies on this combination of interaction and randomness. And as the title of the talk kind of suggests, we're going to focus on this aspect of interaction and how much interaction is necessary. And wouldn't it be really awesome if we had non-interactive zero knowledge, meaning that instead of this back and forth ping pong between the verifier and the prover, the entire interaction only consisted of a single message sent from the prover to the verifier. Very much like an NP statement, the prover is trying to convince you that a graph is three-colorable, sends the three coloring, and that's that. Wouldn't it be great if you could do that in a zero knowledge way? And beyond this basic idea of minimizing interaction, this idea is really, really important in some domains. In particular, in contrast to an interactive zero knowledge proof, if you have a non-interactive zero knowledge proof, it's something that you can say, post on your website. You want to prove a statement, you post the proof on your website, everyone can see it, and that's that. Or, in a more modern era, you can post this proof on a blockchain. And this is something that people are really interested in doing. So wouldn't it be great if we had non-interactive zero knowledge? Right? And the following claim says that we cannot. So what does it say? It says that if you have a language L, and it has a zero knowledge proof in which the prover only sent a single message, the entire interaction consists of a single message sent from the prover to the verifier, then the language L is trivial somehow. It's in BPP. So kind of sad news. Let's see the proof. Well, let me just directly describe a decision procedure for deciding whether this, say, a given input X belongs to this language L. And I'm not sure if possibly Alon showed you this in the morning. In case he did, then I'll just quickly repeat it. So here's the idea. So I'm describing a decision, a BPP decision procedure for deciding this language L. So I'm given an input X. I run the simulator on this input X to get a simulated proof, pi, right, something that simulates what the prover would have sent. And now I simply run the verification algorithm on the input X and the proof that was generated by the simulation. Right, so that's a decision procedure. Let me convince you that it works. Well, for completeness, if X is in the language, then by the guarantee that the simulator kind of simulates the actual interaction, this proof pi will be indistinguishable from what an actual prover would have sent, and therefore our verifier V is going to accept. So, okay, so we have completeness. What about soundness? Well, if X is not in the language, then we know that in general V will reject all proofs, right? That's what soundness means. In particular, one generated by this simulator. Okay, so we have completeness and we have soundness. It means that L is in BPP, and that tells us that non-interactive zero knowledge is trivial, right? We can only have it for BPP. So that will end my talk. Thank you. No, wait. Okay, so the actual model, this was kind of to motivate the actual model, was proposed by Blum, Feldman, and Micali in '88. And the key idea, really, that kind of lets us avoid the impossibility result is something called a trusted setup. And in the most basic incarnation, or the typical incarnation, it's what's called the common reference string model. And the idea is that before all the interaction starts, some trusted party comes along, generates some reference string, some string from some distribution, and this string, which is typically called CRS, or common reference string, is something visible to all parties. Okay, so the trusted party generated it first, now it's visible both to the verifier and to the prover, and the interaction can use that. Okay, and as a matter of fact, it is even preferable and sometimes possible for this common reference string to simply be just a random sequence of uniformly random bits. And this is sometimes called the common random string. It's really confusing because common reference string and common random string have the same acronym. So for this talk, and let me propose in general, let's call it a common uniform random string, or a curse, in case the random string is really uniform. Okay, so this is the model. And let's kind of try to define what completeness, soundness, and zero knowledge mean in this NIZK or NIZK setup. So as usual in zero knowledge or in interactive proofs, we have a verifier who's given an input X. We have a prover who's also given the input X as well as a witness. We have some underlying NP language that we're talking about. Right? And in addition, and the twist is that both the verifier and the prover are given access to this CRS, okay? Which comes from some distribution. Given the CRS, the prover can generate a proof pi, sends it over to the verifier. Now the verifier, given access to the CRS and to the proof pi, can decide whether to accept or reject. Okay, so that's the interaction. Completeness means, as you would suspect, that if X is in the language, then the probability over all coins tossed, in particular over the choice of the CRS, that the verifier accepts is, say, 1 minus negligible. Okay, so almost certainly the verifier will accept. Soundness means that if X happens to be not in the language, then for any cheating prover strategy that you may choose, so let's say an efficient cheating strategy, which corresponds to this notion of arguments that Alon talked about. You can also think of a variant where you're talking about general cheating provers. So for any such cheating prover with high probability over the choice of the CRS and the verifier's coins, the verifier is going to reject the proof sent. Okay, so that's soundness. Questions so far? Okay, and lastly, zero knowledge. So intuitively, it means sort of whatever the verifier can see, we can simulate. Right? That's what we want zero knowledge to capture. And the idea here will be that there exists an efficient simulator so that for all X's that are in the language, the output of the simulator is computationally indistinguishable from what the verifier can see, namely the CRS and the proof string. Okay, so the verifier could have, by himself, generated a simulated CRS and proof string that looks indistinguishable from the real thing. Okay, that's the definition of an NIZK. So before kind of telling you what we can do with NIZKs, how we build NIZKs, just a short philosophical detour of, is this notion that we just defined, NIZK, is it really zero knowledge? And the kind of tricky aspect is that if I give you an NIZK proof, then you can go along and use this proof to convince someone else, right? As long as you're using the same CRS, you can just take this proof, it's a static object, and give it to your friend and convince him that X is in the language, which is very kind of different from what we saw for regular zero knowledge, in which you cannot do this. And in particular, you might argue that you've actually learned something about X, namely, you've learned a convincing proof that you can share with other people that X is in the language. Right, so how can this be zero knowledge? And the way to kind of get around this is that what you've learned is basically something about the CRS. You've learned a convincing proof with respect to a particular CRS. So in essence, what you've learned is about the CRS rather than the input X. But, it's still arguable about, philosophically, is this zero knowledge or not? What I want to point out is if you don't care so much about philosophy, a crucial point is that this notion is very, very useful in applications. Okay? Good, so that's NIZK. And I want to show you why this definition kind of gets around the impossibility result that we saw in the beginning. So, right, this was kind of the claim that we had, but now I'm extending it to the CRS model. So let's say I wanted to prove to you that if language L has an NIZK in the CRS model, then L is in BPP. And I'm just going to kind of copy-paste the same argument that I had before. Okay, so the decision procedure is run the simulator. You get now both the proof pi and the CRS. Now run the verification on X, the CRS, and the proof pi. Okay, that's a proposed algorithm for deciding the BPP language. And if I'm claiming that the notion of NIZK in the CRS model is non-trivial, something has to go wrong. Let's try to find out what goes wrong. So completeness says that if X is in the language, then the simulated proof and CRS jointly are indistinguishable from the real interaction, which makes V accepts. Nothing wrong with that statement, so completeness works. The issue is going to come up in soundness. So the argument in soundness says, if X is not in the language, then V rejects all proofs. But that's true for common reference strings that are kind of correctly distributed. And no one tells us what is the behavior of the simulator when you run it on X that's not in the language. And indeed, it's going to be fundamental that the CRS that the simulator generates on X is not in the language behaves statistically very differently from an actual CRS. Okay, but so the point is that when X is not in the language, the CRS that we generate is going to not correspond to a real CRS, in which case we may have proofs that convince us. And that's why the decision procedure doesn't work. Is the point clear? No questions, so either entirely not or entirely yes. I will hope for yes. Okay, so what can we do with NIZKs? So pretty nice list of things. I want to highlight two of them. The first one, which was kind of one of the first applications of NIZK, and really a fundamental one, is chosen ciphertext secure encryption schemes, shown by Naor and Young, which is kind of both the first method by which chosen ciphertext security was demonstrated, as well as till today, it's kind of the textbook way of showing it. The other, which we'll hear much more about from Eli on Thursday, I believe, and Jens, is something called ZK snarks and ZK starks, and in general applications to cryptocurrencies where you want to prove in zero knowledge, I'll call it maybe that I paid you an amount of money while hiding my identity, and there it's really crucial that it be non-interactive. There, the challenge is even greater, as we'll see on Thursday. Okay, so NIZK is this really important notion, and we'd like to build it. And okay, before building, let's talk a little about a variant of NIZK. I called it the boring slide because it's a little bit tedious. They're going to be a list of 5 different notions. It's not boring in the sense that these notions are actually super duper important for applications, that they're highly desirable. But it's kind of a bit tedious to go over all the notions, so I'll do it kind of quickly. So first thing, a nice property that seems really important is that this common reference string is something that you can reuse across different interactions. So if today I prove to you the correctness of one input X, tomorrow I want to prove the correctness of a different input X, so you can use the same CRS. The definition, as we stated it so far, doesn't guarantee it. We will aim to have stronger variance, but for this talk we're going to stick with the basic notion. So that's multi-theorem NIZK. The second notion is adaptive soundness. So if we're indeed thinking of the CRS as something that's posted once and for all and everyone sees, then maybe I can, based on the CRS, I will try to convince you of a statement that is related to the CRS. Right? If it's something that I already saw, then this is a concern. Adaptive soundness says that I cannot even do that. Analogously, adaptive zero knowledge will say, if I'm trying to learn something about an X that's in the language, and I get to choose X after seeing the CRS, I still can't do that. The definition that we had, as stated, doesn't guarantee it, but it's a highly desirable property. And lastly, and related to Alon's talks, something that we'd like to have is statistical soundness, which means that soundness is guaranteed even if against cheating provers that are not bounded, not just against polynomial time cheating provers as we defined. And we'd like to have statistical zero knowledge, meaning that the output of the simulator is kind of statistically distributed like the real interaction. And often we can get in protocols either statistical soundness or statistical zero knowledge, typically not both. So you need to choose what's more important for you. Okay, so that's kind of, we went through the variants. I want to tell you a little bit about what's known about NIZKs, and then we'll see one of the basically textbook constructions of NIZK. So what is known? And this is, this slide is kind of already outdated. It's from 2018. So we'll see the changes next. But here's what we know in 2018. So again, this textbook's construction, which is what we're going to see, is a beautiful result due to Feige, Lapidot, and Shamir from 1990, which gives NIZK, non-interactive zero knowledge, for all languages in NP, based on a computational cryptographic assumption called trapdoor permutations. The star there is that we need certain variants of trapdoor permutations. We'll talk about that a little bit more later, but basically from trapdoor permutations. So really, anything that you can prove at all, you can prove non-interactively with zero knowledge based on this assumption. It's a pretty amazing fact. In particular, since we can construct trapdoor permutations based on the hardness of factoring large integers, right? I choose two random primes, p and q, give you the product of p and q and ask you for the factorization. We believe that's, or some of us believe that that's a hard problem. Based on the hardness of this problem, we can build trapdoor permutations, and then based on the FLS result, we get NIZK for all of NP. And we're going to see that today. Let me mention some other known results from back in the day in 2018. So from bilinear maps, Groth, Ostrovsky, Sahai can build this. Tomorrow we'll see a result in something called the random oracle model, which is not the CRS model that I defined today. It's related but different. We'll see that tomorrow. Based on very strong assumptions related to code obfuscation, we knew how to do this. And in a sequence of works that I was involved with, we can also do this from kind of what we call optimal hardness assumptions. Again, very strong assumptions. So that was, ancient history. In 2019, we have some new and exciting results. I want to mention them. So work of Canetti, Lombardi, and Wicks from 2019 gave a first construction based on the learning with errors problem. So in particular, based on worst case hard problems on lattices, together with this somewhat annoying thing called the circular security assumption. I don't want to define that. And just fresh off the press last week, Peikert and Sehisen, I hope I'm pronouncing the name correctly, showed that we can do this from vanilla LWE, which was kind of a pretty important open problem for over a decade. So that's kind of exciting. It also goes to show you that there's active research, very active research, I would say, on these problems. And still a lot more to discover. In particular, two open questions that I wanted to mention. One is that we currently don't know how to construct NIZK from kind of discrete log type of assumptions, things like the decisional or computational Diffie-Hellman assumptions in groups that don't have a bilinear map. That's open. And from even, that's maybe somewhat accessible, harder questions, can we build this from a generic assumption? Say, can we build NIZKs from one-way functions, like we could do for, interactive zero knowledge? And that is, as far as I know, as far as I know, and I know, it's wide open. As far as I know, there are no real barriers to this. So there's no reason for us to believe that it's not possible. Okay. Great. So let's go back to 2018, and the result that I want to show you today is a construction of NIZK for all of NP based on hardness of factoring or based on trapdoor permutations. Okay, so that's what we're going to focus on for the rest of this talk. So the construction, this result by FLS, the construction has two main steps. The first step is going to be to construct an NIZK in something that's called the hidden bits model, which I'm going to define in the next slide. That's step number one. That step is entirely information theoretic, no assumptions, it just exists, such an NIZK. The second step is going to be a compiler that takes any proof system in the hidden bits model, in particular the one that we constructed in the first step, and transforms it into an NIZK in the standard model, meaning the CRS or common reference string model, even in common random string model. Okay. So what is this hidden bits model? So it resembles the CRS model, but it's different, and I want to kind of be sure that the difference is clear. So as before, we have a verifier and a prover. Both get X. The prover also gets the witness W. And as before, we kind of have this string in the sky. But the string, we call it the hidden bits for a reason that's going to be clear in a second. And only the prover gets to see these hidden bits. However, the prover, so given these hidden bits, or given this string in the sky, X and W, the prover generates a proof pi. But in addition to the proof pi, it can specify some subset of these coordinates in the sky. And only for those coordinates, the verifier now gets to see their values. So one kind of way to put it is, we have these hidden bits in the sky. They're all kind of covered with clouds from the perspective of the verifier. And I guess the prover has some sort of a laser or something that it can point at particular clouds to clear them up, which allows the verifier to see particular points in the string. Okay, so I hope the difference between a plain CRS model in which both the verifier and the prover see the entire string and this hidden bits model is clear. If not, and again, you can stop me at any time. Okay. Right, so the difference is that the verifier only gets to see a part of the CRS, and the prover can, potentially maliciously decide what part of the CRS the verifier gets to see. Okay, good. So that was the model. We now have two steps. First, I want to show you a construction of NIZK in the hidden bits model. That's step number one. Step number two is this compiler moving from any proof system in the hidden bits model into a full-fledged NIZK and the vanilla CRS model. Okay, so here's the construction. And we're going to start off, we want to show a general result for NP following what Alon showed us earlier today. We're going to use our favorite problem, which is Hamiltonicity. It's an NP complete problem, so that will be good enough. So again, the problem, if you dozed off in Alon's talk, the problem is, you're given a graph G, and you're asked, does it contain a Hamiltonian cycle? So a path going along all vertices in the graph. We're going to construct a hidden bits model for this problem. Since it's NP complete, we get all of NP. Just a couple of things before telling you what the construction is, a couple of interesting facts about it. So it's information theoretic. There are no cryptographic assumptions. The prover strategy is going to be polynomial time. If you give it the graph and the cycle, it's going to run in polynomial time. We're going to get perfect completeness. So true statements are accepted with probability 1. Somehow, surprisingly, we're going to get perfect soundness, which means, and this is even against the computationally unbounded prover, meaning that for any proof, forget about the prover, for any proof string, the verifier is simply going to reject it. Okay, which may sound somewhat surprising. We'll talk about, so this we can only get if we're talking about a common reference string model. If we talk about the common random string model, which is what we're going to care about more, then the soundness will become statistical rather than perfect. They're going to be an exponentially small cost in moving to a common uniform random string model. Okay, so what's the idea? So we have a common input. It's a graph G with vertex at V and edges E. The prover also gets a Hamiltonian cycle, so some subset of the edges that form a cycle going through all vertices. The CRS, I need to specify what distribution it comes from. So it's going to be just a random cycle graph. Okay, random graph that just has kind of random cycle going through all the vertices, but a random such graph, no other edges. And the representation is going to be via the adjacency matrix. Okay, so n squared size CRS string. Or rather, I shouldn't have called it CRS, it's kind of these hidden bits, right? We're in the hidden bits model. Right, so we have both guys get the graph G, the prover gets the Hamiltonian cycle H, and they have access to a random cycle graph C. We'll denote the vertices of C by VC and the edges as EC. And here's the idea. So the prover is going to find an injective mapping the vertices of our graph G into the cycle graph so that this mapping preserves the cycle structure. Okay? So since both contain a cycle, there is a way to do this. Both H is a cycle and C is a cycle, there is a way to do this. And he's going to reveal a subset of, so remember that so far the verifier is unable to see anything here. Now the prover needs to decide where to shoot his laser. So the edges that he's going to reveal are going to be all the kind of entries in the matrix, in the adjacency matrix, that correspond to none edges of the original graph G, right? So notice here, I'm looking at V squared and removing E. So these are all the none edges of the graph G, and applying the mapping here. I define the mapping as mapping vertices. You can extend it to edges in the natural way. So here I'm looking at, I have my original graph G. I'm looking at all the entries that are non-edges, looking at where they map to in my cycle graph, and revealing exactly those entries, which of course should be none edges also for the cycle graph. Okay, we'll see why this is good in a second. What can the verifier do? Oh, sorry, and of course the prover sends over the mapping pi and sends over, specifies this set S, and now the verifier can read this set S of points from the adjacency matrix of the cycle graph. What does the verifier do? Well, first of all, given pi, this mapping, he or she checks that pi is an injective function, right? And second, he checks that indeed for all the none edges of the original graph, if you apply the mapping, this none edge from the cycle graph was revealed and is indeed a none edge. Okay, so in these cleared up skies, what he sees is a 0 or a none edge. Okay, and if both of these checks pass, then the verifier accepts. So let's see why this works, and let's start off, we need to show completeness, soundness, and zero knowledge. So let's start with completeness. So let's bring back the protocol. What does the verifier check? That this pi is injective. Well, it is indeed injective, since that's what the prover did. So that's fine. And he checks that for every none edge of E, the edge mapped by pi was revealed and is a none edge. And indeed, this is exactly what the prover does. And so both checks pass, and the verifier accepts with probability 1. So that's good. That was easy. What about soundness? A little bit more tricky. So let's suppose for a second that V accepts. Forget about whether X is in the language or not. Let's just assume that V accepted. Well, based on the checks that V does, it means that A, this mapping pi was injective, and B, that all of the none edges of E were revealed, because that's what explicitly the verifier checks. So let's think now about the inverse E prime of all of these cycle edges of our graph C from the CRS, or from the hidden bits. And observe that, first of all of these, this set E prime, this inverse, has to actually contain edges, because none of these were revealed. Right? So E prime is actual edges. It cannot contain any non-edges in the original graph G, on the one hand. And on the second hand, because it's an inverse using an injective mapping of a cycle, it itself has to be a cycle. So bringing together these two facts, what we get is that E prime forms a Hamiltonian cycle in the graph G, meaning that G is Hamiltonian. So if G were not Hamiltonian in no instance, the verifier, the conclusion is that if G were not Hamiltonian, then the verifier could not have accepted. And we're in the very rare case where we can get perfect soundness. And as a comment, which I essentially already says, is that this worked when the CRS was, a random cycle graph. It's not immediate to see how you can generate a distribution of a cycle graph using only uniform random bits. You can do this, but there is a cost, and the cost is an exponentially small soundness error, which is also inherent. So if you want a uniform random string, then there is some exponentially small soundness error that you lose. Question? Can you a little bit louder? Yes, sorry. So E prime was the inverse. So we know that the CRS contains a cycle graph, right? This is not up to the CRS, both in the soundness and completeness conditions. The CRS, we know what it is. It's a random cycle graph. So we know that there is a cycle C, and we know that we have a mapping pi, which is injective. So I'm going to look at the inverse of the cycle. I look at the cycle C, I apply the inverse of pi, and I get a bunch of edges in the original graph. More questions? Okay. What about zero knowledge? Well, just on the intuitive level, what does the verifier even see? He sees this mapping from the vertices of V to the vertices of the cycle, and he sees that all of the non-edges of G were revealed inside the cycle, right? Or rather, the mapping of the non-edges was revealed. And intuitively, this doesn't tell him anything about the actual cycle. And to formalize, we're going to show a simulator, which works as following. So the simulator is given a graph G. What it does is choose a random injective function from pi to say numbers between 1 and n. Okay, so random function. And its output is going to be this random mapping. And now it takes this mapping, applies it to the graph, and gets, gets a mapped graph. And it's going to set the set S to be all the non-edges of the mapped graph that it generated. And it's going to reveal all of these non-edges. That's what I mean by setting that the CRS located at S, which is what the verify actually sees, and what I need to simulate here, just contains zeros, meaning non-edges. Okay, so that is what the simulator does. And why does this actually simulate the real thing? Well, the first claim is that if you look at any fixed injective function pi, if you look at the simulated view, then I claim that it's going to be identical to the real view. Why? Because in both cases, all you see is, take pi, apply it to your graph, and open up all the non-edges, right? And the second claim is actually the distribution of this random function pi is the same, right? In the simulation, it's just a random injective function. In the actual claim, it's the function that you get by taking a random cycle graph and looking at the kind of the injective function that maps you from the cycle in G to the cycle in the random graph. And you need to argue that this generates the same distribution. It's relatively easy, so I won't do that here. Okay, but combining these two claims together, you get that the output of the simulator is identical to that of a real interaction. Okay, so that gives us our construction of NIZK in the hidden bits model. And the second step that I need to show you is a compiler taking any proof in the hidden bits model, in particular the one that we just saw, and making it into a standard full-fledged NIZK. Okay, but for now that we've kind of constructed the NIZK in the hidden bits model, we can forget about how it worked. If I lost you, then you can come back now. We want to show a generic compiler taking any hidden bits NIZK and making it into a full-fledged one. So how does it work? Right, so we have our hidden bits model. It's kind of this somewhat fictitious abstraction. It's not that we actually have these clouds and lasers in real life. And we want to use cryptography to kind of simulate the lasers, essentially, and get a construction in the standard CRS model. And the tool that we're going to use, as I said before, is this notion of a trapdoor permutation, which I want to define for you. So what are trapdoor permutations? And actually, the definition that I'm going to present today is somewhat of a dream version of trapdoor permutations. In particular, and somewhat sadly, the actual candidate constructions that we have don't satisfy this dream version, which is somewhat unfortunate. And in particular, it causes massive headaches in the actual compiler from hidden bits to non-hidden bits. So that's sad, but it's kind of for me to worry about and you kind of not to worry about. So it's really annoying. That's the sad news. The good news is that it generates a lot of papers. So if you're interested, you're welcome to ask me or look up some of these works, and I can tell you the exact references offline. Okay, so what is the idealized notion of trapdoor permutation that I want to deal with? So here it is, and it's kind of related to one-way functions and one-way permutations. So the idea is that it's a collection of permutations, efficiently computable permutations, right? So I have a collection indexed by alpha of permutations, P sub alpha, where each permutation is a permutation over 0, 1 to the lambda. Lambda just denotes a security parameter for me, okay? So we have a bunch of permutations, all of them working on 0, 1 to the lambda, mapping 0, 1 to the lambda to 0, 1 to the lambda. And every string alpha in 0, 1 to the lambda describes such a permutations. So we have 2 to the lambda permutations, each permutation working on a domain of size 2 to the lambda. And they're all efficiently computable. So given alpha and an input x, I can compute P sub alpha of x. Okay, so so far not so interesting. That's kind of just the syntactic requirements. In addition, I also, crucial thing that I want is that, so of course anyone can go along and generate alpha by just choosing a uniform random string of lambda bits, but I want there to be kind of another more fancy algorithm that manages to generate a uniformly random alpha together with a trapdoor tau. And we'll see in a second what this trapdoor lets you do. But before that, kind of the security requirements of trapdoor permutations, to be succinct about it, simply says that if I give you a random alpha, and so I choose alpha at random, choose x at random, give you alpha, and give you p sub alpha of x, it's going to be computationally difficult for you to recover x. Even though notice that x was fully determined, right? We said that p sub alpha is a permutation, its inverse is defined, so x is information theoretically determined, but it's hard for you to find x, given alpha and p sub alpha. The cool thing about trapdoor permutations is that it turns out that it becomes actually easy to find the inverse if I also give you the trapdoor. Okay, and hence the name. So if I give you the trapdoor tau, and I give you, and now x can be arbitrary. So even in the worst case, if I give you tau and p sub alpha of x, now you can efficiently recover x. So given only alpha, you cannot invert. Given tau, in the average case, given tau, you can invert even in the worst case. Okay, so examples for this, we don't have many, essentially two. One is the famous RSA function, and another almost as famous but not as quite is the Rabin collection, which is just a squaring mod, a product of two primes. Okay, the reason that it has a star here is, as I said, they don't satisfy the idealized notion. They satisfy some relaxation of it, which turns out to be good enough for applications. Okay, the last cryptographic ingredient that I'm going to need is a hardcore predicate, which I kind of assume or hope that you guys have seen. But in the context of a trapdoor permutation, this is an efficiently computable function mapping our domain 0, 1 to the lambda to a bit, 0, 1, so that given alpha and p sub alpha of x, not only can you not recover x, you cannot find h of x with noticeable advantage over 1/2. Okay? So h of x is hidden from you, and we have a generic technique of getting a hardcore bit for any trapdoor permutation. This is the Godric-Levin theorem. Okay, so we want to use these idealized trapdoor permutations to implement the hidden bits model. And we're going to start with kind of a bird's eye of what's going to happen, and then kind of a very detailed view. So here's the bird's eye. So our CRS, right, we're now implementing, we're kind of describing a full-fledged NIZK and the common random string model. So the CRS is going to consist of L different Ys. Okay, we'll see soon what L needs to be, but a bunch of Ys, which I think of as being kind of in the codomain of the permutations or range of the permutations. So a bunch of Yi's. And the way the protocol is going to work is that the prover is going to choose alpha and tau. The hidden bits will be simply defined as the hardcore bit applied to the Yi's, which intuitively means that they're hidden from, actually it should be the hardcore bit applied to the preimage of the Yi's. So this is a typo. Here this should be, instead of Yi, this should be P sub alpha minus 1 of Yi, or yeah. And then to reveal if the prover decides to reveal one of the bits, he can simply send the preimage, and then the verifier can check. So this was the bird's eye. Let's see the detailed view so everything is clear. So the frog's eye view of the protocol. All right, so we have our verifier and we have our prover as usual. As I said, the CRS consists of a bunch of these Ys, a bunch of these Yi's. What does a prover do? So he chooses a description of a permutation alpha together with a trapdoor tau, and he sets xi's to be simply the inverses of the yi's. So he looks at all of these yi's up in the sky and takes their inverse under p sub alpha. Now we define the hidden bits this time correctly as h applied to these xi's. So the ith hidden bit is simply h applied to xi. Now that our hidden bits are defined, we can run the hidden bits prover, right? That hidden bits prover, what he or she likes to see is the input x, the witness w, and this list of hidden bits. So we've defined them, b1 up to bl. Now the hidden bits prover responds with a proof pi and with a subset of bits to which we want to point our laser, we want to open. And what the prover sends is the index alpha of the permutation, the proof pi that the hidden bits prover wanted to send. And in order to reveal, to replace the laser, he sends xi's for all locations in S. And we'll see that that allows the verifier to learn these hidden bits, to kind of unravel the hidden bits inside the set S. So what does the verifier do given all of this? So first of all, he checks that alpha is in the collection. We said that any string of length lambda is valid, so just that it's a lambda bit string. Turns out to be important, and is especially important when we're talking about non-idealized versions of trapdoor permutations. But for now, it's an easy check. The verifier then checks that for all of these indices that we wanted to open, he checks that indeed the xi's that he got over here, the xi's that he got over here are indeed the preimages of yi under the permutation p alpha. And he can do this by simply taking xi and applying the permutation. Okay, this is something that anyone can do. Now, also the verifier, from his perspective, can define the hidden bits as the hardcore bit of the xi's. And he runs the hidden bits verifier. What does the hidden bits verifier expect? He expects the input x, the proof pi from the hidden bits model, and to see these unraveled bits bi for bits in the set S, okay, which we have indeed computed. We have these bi's for all I and S, and we can run the hidden bits verifier. Okay, so that's our protocol, and let's try to quickly see why it has completeness, soundness, and zero knowledge. So first of all, completeness. Let's bring back the protocol and check that all the checks that the verifier does when X is in the language and the prover behaves in this way actually pass. So is alpha in the collection? Of course. That's what the prover sent. For all I and S, if you take xi and apply the permutation, do you get yi? Sure, because xi was defined specifically in this way. And then, what we do here is a direct reduction to the completeness of the hidden bits verifier. They're using the same bits, right, B1 up to BL over here, the subset of those inside S, and by the completeness of the hidden bits proof system, we will get perfect completeness also here. So that was easy. Now let's do zero knowledge and then go back to soundness. So how do we argue zero knowledge? Well, intuitively, just intuitively, the bits bi for I inside the set S are revealed, but by the hardcore property for the other bits not inside the set S, we didn't reveal those xi's, and therefore, again, by the hardcore bit property, those bi's will remain hidden. And the proof crucially uses that. Let me kind of describe the simulator pretty formally. I won't go through the entire argument of why the output of the simulator is computationally indistinguishable from a real interaction, but it basically relies on a combination of the hardcore bit property together with the zero knowledge of the hidden bits proof system. Okay, so what does the simulator do given an input x? So first of all, it runs the hidden bit simulator. The hidden bit simulator gives it a proof pi, a subset S, and a bunch of revealed bits for corresponding to that subset. Now the simulator samples trapdoor permutation together, index and trapdoor. And for all the bits I inside S, it's going to sample xi so that h of xi is equal to bi. How does it do that? Well, just rejection sampling. It samples a bunch of x's until one of them, if it wants bi is 0, we'll just sample a bunch of xi's until it hits 1, for which h of xi is 0. For those i's inside the set S, is going to define yi to be p sub alpha of xi. Now, for i's that are not in S, it can just sample yi's at random, right? And it outputs, the permutation, kind of the view of the verifier. So which includes the description. This is all the first sequence of things inside brackets is what the prover sends. So it's an index of a permutation, the proof pi from the hidden bits proof system, and the revealed set of positions S. And this is the CRS. So Y1 up to YL where we call that for i's in S, the yi was sampled in one way. For i's not in S, it was sampled in a different way. And it's not too difficult to show that this simulation is computationally indistinguishable from the real thing. Okay? Good, so we have zero knowledge. Now let's talk about soundness. And to argue soundness, let me go back to the protocol, actually. To argue that soundness holds, to argue soundness, I need to consider what an arbitrary cheating prover does. But I want to kind of start off with the weakened version, in which I insist that the cheating prover P sends some particular string alpha in its message. Okay, and later we'll need to generalize to provers that are allowed to send anything. But for now, I want to kind of fix alpha and think of a cheating prover that has to use this particular alpha and argue soundness. Okay, so I want to assume that our alpha is fixed. Once alpha is fixed, we can kind of define the hidden bits. Just kind of as a mental experiment, I want to define the hidden bits as, this f should be p, but the inverse of the yi's. The yi's are what we have in the CRS, and we apply the hardcore bit to these yi's. And now, let's maybe go back to the drawing. It's useful. No. Okay. So I've constrained my prover P to send some particular string alpha. Now if the verifier is going to accept, the BIs are entirely defined, right? And now we can rely on the soundness of the hidden bits proof system. Okay, you can actually show a reduction, but I think intuitively should be clear. Okay, so for any particular choice of alpha, the hidden bits are entirely determined, and therefore we can rely on the hidden bits soundness. Okay, but the problem is that, in general, the prover can choose any old alpha that it likes. It doesn't have to choose any particular one. And indeed, this, So soundness holds for this fixed alpha, but if you think of it, if the prover has the flexibility of choosing alpha by itself, for every alpha there's a different sequence of hidden bits on which you can potentially choose and on which you can potentially decide to cheat on. So instead of kind of having one sequence of hidden bits, he has 2 to the lambda different options for hidden bits, for a string of hidden bits, each corresponding to a different choice of alpha, which seems like a problem. But thankfully, there's a simple way to resolve this. And the idea is the following. So our hidden bits proof system, we're going to repeat it enough times so that the soundness becomes very, very small. So let's say 2 to the minus 2 lambda. Is that a question? So the hidden bits proof system, we can repeat the entire thing many times. The soundness is going to go down exponentially fast. In particular, if you repeat it 2 lambda times, the soundness error is going to be 2 to the minus 2 lambda. And now, what is the probability that there exists some alpha on which the prover can cheat? Well, just by a union bound, this is at most, the sum over all alpha times the probability that the prover can cheat on this particular alpha. And for each particular alpha, we saw that it's 2 to the minus 2 lambda. And we have at most 2 to the lambda different choices of alpha, which means that overall the probability is at most 2 to the minus lambda, which is negligible, and we're happy. Okay, so the trick to get around this was simply to amplify soundness and apply a union bound. Pretty common technique. It's somewhat surprising, I think, when you see it for the first time. Okay. So we have soundness. And just to summarize, this is the last slide. Just to summarize, what do we have? So from factoring, we didn't see this, but this is a standard thing. From factoring, you can build trapdoor permutations. This is the Rabin collection. We saw an unconditional hidden bits NIZK for Hamiltonicity, and therefore for all of NP. Taking these two together, we saw a compiler that builds NIZK for all of NP. In particular, we obtained the theorem that if factoring is an average case hard problem, then all of NP has NIZKs, and now I'll end for real.